Okay, so after so much of trouble, internet is still not working, but we have to continue. So let's start with okay, so after so much of trouble, this one.
Am I late to the lesson is late? Am I late to the lesson is late?
Both. Is it?
Has it started yet?
Can't hear you.
Has it started yet?
He is
Okay,
trying,
so
but there's no internet.
let's start with a new chapter. So in the last 2 weeks, we have studied that how we're going to use search problems to find a certain goal. But today we are going to start a new chapter which is called knowledge-based systems. And we will see that in case of search algorithms, although we were trying to go towards goal, for example, we were taking Manhattan distance or we were taking straight line distance, but still we are not sure about the complete information about the problem. So it means that search algorithm can be a portion of AI, but to develop all the underlying information about any problem, we need some more knowledge. For example, we came to know that the distance from one city to another city was certain thing. How we came to know that? We never thought about it. So it means that we need some knowledge to gather all that information and then apply certain algorithms. So in this case, we say that we have knowledge-based systems. From knowledge-based systems, somehow we can think of that they have certain amount of knowledge, they have certain amount of information, and based on that information, they act on something. So that's why we say that we have a knowledge base, KB, which is the main central component. And then within knowledge base, we have some information. That information is called sentences. Sentences here are not like English sentences. Here sentences mean any logical information about the problem. So it means that we have a knowledge base. Inside knowledge base, we have a lot of sentences. What does it mean? It means that we have many logics, and using those knowledge, using those logics, we can do something. So here we say that we need knowledge-based agent. They reason by operating on internal representation of knowledge. So we have an internal database, and then based on that, if for example I say if it is raining, I will not go outside. So this is my database. So next time if someone say that it is raining outside, so I can from my system I can say, okay, if it is raining outside, someone is not going outside. So based on certain representation of knowledge, knowledge-based agent takes an action or do something. If we go a bit more generic definition, we say that a generic knowledge-based agent given a percept. Percept is any input. Like I said that in this case, I came to know from some sensor or something that it is raining outside. So given certain input, the agent adds the percept to its knowledge base. So it will take that input, then it will compare with its knowledge base that what would be the action. Ask the knowledge base for the best action and tells the knowledge base that this action, in fact, the knowledge base that it has in fact taken the action. So it means that it has certain rules and regulations, then it will take certain input and then follow that rules and regulation. If for example, we take in one of the example for the vacuum, so if vacuum is moving and if the sensor is telling that there is dirt on the floor, then based on that, what it will do, it will either clean it, or if for example the input was that I have already covered this certain area, then based on the knowledge base, whatever we have defined inside, we can take certain action. Okay, if for example there is an example here, so it means that based on certain knowledge base, we can do certain reasoning, we can do certain conclusions, we can draw certain conclusions. So here we say that if it did not rain, Tyrion visited Bronn today. Then, so it means that in knowledge base, as I said, that we will be having some knowledge. Then Tyrion visited. Okay, so Tyrion visited Bronn or John today, but not both. So the first information was that if it is not raining, Tyrion will visit Bronn. And then the second information was Tyrion can visit only one person, either Bronn or John. Then the third statement was Tyrion visited John today. So from that, what we can draw conclusions for the final, based on all these statements, there is one statement which says Tyrion visited John today. So it means that if Tyrion visited John today, then it means that based on this statement, Tyrion cannot visit Bronn, right? Because Tyrion can visit either John or Bronn. So it means that if it has visited John, it cannot visit Bronn. And similarly, there is a second argument that we can take from it is, since Tyrion visited John today, and we said that if he is supposed to visit Bronn, it is not raining, but he visited John, so it means that it is raining. I don't know what is happening.
Slides up another timer, maybe.
Is it PowerPoint slide? Sorry? Is it PowerPoint slide?
Yes.
I think the timer is set for like.
Uh-huh. Okay, so it means that we have said we have, just to recap because it was so much troubling. So we are studying here a knowledge-based system, and we say that what is a knowledge-based system? So any system or any agent which has certain internal knowledge, and based on that knowledge, if we provide certain input to it, it will compare with its internal database and then will take certain actions. So that's why we say that based on an internal representation of knowledge, it will take certain action by processing the inputs. Here was an example where we say that what can be a knowledge base? Knowledge base can be, for example, we say if it did not rain, Tyrion visited Bronn today. Then there is another statement in the knowledge base which says Tyrion visited Bronn or John today. It means that it can visit only one at a time. And then there is the final statement which says Tyrion visited John today. So it means that if you process all of them, what information we can get, what extra information we can extract. Here it says that Tyrion visited John. So it means that it cannot visit Bronn because it can visit only one at a time. So it means that the first statement that we can draw is Tyrion did not visit Bronn today. And if it did not visit Bronn today, the condition was if he was supposed to visit, it was supposed not today. But since he's not visiting Bronn, it means that the other information that we can extract from it means that it is raining today. So based on that, we can say that a knowledge base consists of certain sentences. For example, this was one sentence. Sentence is not, as I said, it's not an English sentence, it is any logic that you know about a word or about a certain problem. Any information that you know would be referred to as a sentence. A sentence is an assertion about the word in a knowledge representation language. A sentence is how AI stores knowledge and use it to infer new information. So in the previous case, you can see that we provided certain sentences, they were given in certain language, and then based on that we can get certain new information. As I said that previously we talked about search problems, but we were just saying that okay, move towards goal based on certain elements. But how to formalize the whole problem, we did not cover that. So it means that, for example, we are saying that we are taking distance from one city to another city. So we need to formulate that problem. We need to tell our agent that by gathering certain information that these are the distances, and then we need to tell the agent that okay, if the distance is less, then move to this, then move to this. So it means that if we talk about the search problem, which we covered in the previous lecture, what is required? It is required that we develop a knowledge base or we develop a problem, then apply a search algorithm and then execute the problem. So previously we were having certain kind of information which was already there. We did not bother from where it came, path, cost or different things, but for a complete AI to work, it should have a knowledge base which consists of all the formulation about the problem and then take certain actions. So, in other words, like I said that sentences or anything about the problem, but in knowledge representation language. Knowledge representation language means this sentence is a knowledge representation language because it is representing certain kind of information. So inside a knowledge base, we have sentences. And how sentences are written? They are written in knowledge representation form. Okay? So it means that the very first step about any problem in AI would be defining all the possible information about your problem. It means that you need to define knowledge base based on knowledge representation, which will be essentially sentences. How this knowledge base would help us? If you have a certain problem, this knowledge base would help to identify which path you should follow to solve your problem. So it will add to your any algorithm while you're searching or if you're doing anything. So it means that your algorithm is strictly dependent on the knowledge base. if your knowledge base, or in other words, if the description or formulation about the problem is good, it would be like an open door to the solutions. On the other hand, if your knowledge base is not very good, or if you have missed certain information, or if you have, for example, if you have calculated distance wrong, then this knowledge base would prevent you to get to the solution. So that's why in one case we say that if knowledge base is good, it would be an open door to problem solving, and in the second case, if knowledge representation or knowledge base is not good, then it would be a kind of wall towards the problem. So you are unable to solve the problems. Now we will keep on moving through all the slides, and we will go through some of the key terminologies and how we're going to use them and what are they. So the very first thing is called propositional logic. Propositional logic, it says logic. It can be true, it can be false. So it means that any sentence, whatever sentence you are defining, you can say either it is true or either it is false. So for example, I am saying it is raining, right? So I can say it is raining is a true information, mean it is 1. So it is not raining would be 0. Or in other words, if I say it is raining is false information, then it is not raining would be a true information. So it means that propositional logic would define all the sentences with certain information, which will give you either that piece of logic is true or false. So that's why we say that propositional logic is based on propositions, statements, in other words, sentences about the word that can either be true or false. For example, I said it is raining. Now, it can be raining or not. For example, I said that if it is raining, Faraz will go outside, right?
Yes.
This is an example. So it means that if it is not raining, then it means that it depends that what is the situation outside. Based on that, your sentence can be true or your sentence can be false. Normally, every sentence we denote it with symbols. For example, we say that it is raining, so we can denote it with P. We can denote it with Q. We can denote it with R. So any sentence, again, sentence is not English sentence, it is a logic about your problem. We can represent it with any variable. This variable would be uppercase. In addition to P, Q, R, it can be like W in subscript 1, 3. It can be facing east. It can be any word, but a single word or variable. Normally, it's easy to represent them with small letters, so that it is easy for you to build the logic. If, for example, P was raining, Q was certain other information, R was certain other information. So if I say, if P is true, Q is true, there is certain thing. So it means that it would be easy to develop a logic, or if we say that it would be easy to develop our code if we have symbols like this. And in some cases, like I said here, I said complex sentences. So it means that if P is a certain sentence, if it is raining, then Q is a sentence that Faraz will not go outside, right? Okay. So it means that P is one sentence, Q is another sentence. But when I combine them together, when I made a condition, this is a complex sentence. So it means that why we are doing this? We are trying to see that based on any input given to a certain agent, how it will respond to that input considering its own knowledge base. Its knowledge base can be anything. For example, I said if a vacuum is moving, vacuum will sense dirt, then it will send it to your knowledge base, and your knowledge base will say, okay, take the dirt out. Then it will do something. So it means that complex sentences will be written with the combinations of multiple sentences with some connective logics. For example, here I said, if it is raining, Faraz will not go outside, right? If it is raining,
Regardless, we have to send cross out.
Yes. Okay. If it is raining and today is Tuesday, something will happen. So it means that now I have introduced an operator. If P is true, if it is raining, if it is Tuesday, Q is true, means in between you have AND. So if you have studied digital logic design, so there is an AND gate. So if one is true, other is true, only then the output would be true. So it means that based on certain samples, based on certain sentences, we can make complex sentences so as to train our system or our AI agent as much as possible. Okay, now in case of connectives for complex sentences, we have 5 types of connectives. The very first one is NOT, and NOT will be represented by this symbol. Then we have an and you can see that AND is represented like this, it looks like an A. So for AND we use this symbol. Then we have a symbol for OR, then this is symbol for implication. Means if A and B is true, implies this. And then there is a biconditional, mean if A and B is true, implies this, or if something is on the right hand side, it can imply to the other. I will get into more details that how they will look like. So moving to the very first one, it says not. A sentence such as not of P is called negation of P, which is true, right? It is a not gate, basically. So if we say P, if we write P, normally whenever you want to write a certain logic gate, so what you do, you simply put 0, 1, and then you see that how is the output, right? So in this case, if for example, I will write P, so here P has 2 states, either false or either true, 0 or 1. And what would be negative of P? If P is false, negative of P would be true. If P is true, negative of P would be false. So it is like a NOT gate. So based on certain input, it can decide certain output. Okay. And later on, you will see that while we are doing this, we are trying to converge towards making our system intelligent to respond to certain things. Okay. Then the second one is AND. A sentence whose main connective is AND, such as W, any sentence, and B is called conjunction. And so in this case we have 2 parts, W and B, conjunctus. So it means that in this case your AND logic will be applied. So like I said, if it is Tuesday and if it is raining, X and Y will happen. Okay. So now it means that in this case we have 2 sentences which are combined together. Again, if you want to write logic, so we know that if you have 2, so 2 power 2, 4 logics, 4 combinations can be made. Means both of them are false. Q is true, P is false, false, true, true, true. And how we write it, you all may know 0, 1, 0, 1, 0, 0, 1, 1. Okay? This is how we write it. Since it follows an AND gate logic, so it means that if P and Q are false, output would be false, right? I mean, both of the conditions are not true, so their AND would result that is not true. Again, here Q is true, but P is false, but we want AND. And the only condition here that would be true is the P and Q. P is true, Q is true, your output is true. This is what this AND gate defines. What if we say that this P was this? If we say that the finally here instead of P it was P naught. Instead of P it is P naught.
Which is 0.
So which one will be true in this case?
Because the P not was P not.
No. So it's like and Q, right? So it would be the second one, right? Why? Because okay, so it would be the second one. Why? Because now instead we in this AND logic we have P naught, so this naught would be 1 when P is actually false, right? So it means that in this case the second one would be true. Depending on whatever you have here, simply put false or true value, and we know that if you put 0 here and if it is complemented not, then 0 would become 1, and 1 times 1 AND gate would give you 1. So that's why it would be the second case. Okay. Right. Now moving further, or a sentence whose main connective is V, or such as W, V, P. So in this case, OR logic will follow. It means that if either of the input is true, if it is raining, or if it is Tuesday, I will go outside. Okay, so false means it's false. If it is, so it is not raining, but it is Tuesday, true. It is raining, it is not Tuesday, true. If it is raining or if it is Tuesday, output is true. So it means that this is how the OR gate works. The next one is a little bit complicated, but we will see how we're going to interpret it. So we are left with two more. One is implies and then other is biconditional. A sentence such as W. So here you can see that you have a complex sentence. So it means that on left hand side you have something. So implies says that if, for example, P implies Q. So whatever is on the left hand side implies to the right hand side. So on the left hand side you can see that you have something which is an AND, right? So consider it like something X, where X we know that is an AND of W and P. So it means that this implies that it's called implication or condition. And here what does it mean? It means if this, then is Z. So if it means that if this is true, if this has some value, then Z would exist. Implications are also known as if-then statements. Like in programming we use if-then statements. So here, if this, then this. Right. So how we, in some books you will also see for implication you have this, or you have simply single arrow or this type of arrow. So all of them are true. How we interpret it? Again, as I said, if I take an example of P and Q, I don't take it. I don't just take it P and Q so that both sides are single sentences and it is easy to understand. So P is one sentence, Q is another sentence. Again, all the possible combinations I have written: false, true, false, true, false, false, true, true. Now, what would be P implies Q? As I said that in this case we have 4 combinations. So here I have written a statement which is very important to understand. P implies Q is saying if P is true, then I am claiming that Q is true. So if P has certain value, then Q is true. If P is Q is true. Otherwise I am making no claim. So if P exists, there is certain claim. And if P is true, Q is also true. And the only way for this sentence to be false is if P is true but Q is false. So it means that if P is true, Q is also true. But the only possibility where this, if we read it in this term, that if I am making a claim that if P is true, Q is true, the only case where this claim can be wrong is if P is true but Q is false. So this would be the only case where in the truth table we will be having a false condition, except that it would all be true. That means that if P is false, Q is false, meaning both imply the same thing, true or false. So it would be true. Similarly, you can see that if P is true, Q is true, output is again true. So these were the two cases. If P is false, Q is true, still it would be true.
Why?
Yes.
Is there any equation to get it?
Sorry?
Do you have any equation to get this?
It's logic based, isn't it?
No, it's not equation. It's just logic based. I know it's slightly difficult to understand. So for this, I would definitely recommend you. There is a short paragraph in the book. You should definitely read that because it's very difficult to explain. But if you will see, there are multiple examples given in the book. I hope that you will understand. Even if not, then you have to trust that this is true, whatever it is here, okay? So again, P implies Q says that if P is true, then I am claiming that Q is true. Otherwise, I am making no claim. So it means that the only possibility where it can be false is only this portion where I am saying that P is true but Q is false. But from this analysis, there is one important thing that we can say from implies that we have all possible conditions. One is very important here, where we say that if the left hand side is true, the right hand side must be true from implies, which is the normal definition for an implies. If we say that A implies to B, it means that A is equals to B, or if A is true, B is true, right? Then finally is biconditional logic. Previous case, if and then. If this happens, this will happen. But in this case, here we say that it is if and only if, IFF, if and only if. And we write sentences in this form. Again, we have all the four possible combinations. So in this case, P and Q is true if and only if P and Q both are true or both are false. So in this case, this is if and only if condition. Previous case, if and then condition. P is false, then Q is false, so it is true. If P is true, previous case, if P is true, Q is false, no, this is not implication. So this is how maybe it would be easy to understand if we get it from the logic of if and then or if and only. So in this case, you can see that you get true condition here and you get true condition here, except that the other two conditions are false. Now, if we move a little bit further, we define sentences, we define connectives. So it means that whenever we are going to build any logic base, it would be combination of sentences joined together using any connectives. And then if you have any input information based on all those connections inside your knowledge base, you will do something. Now, moving a little bit further, like I said that if we say P is one sentence, Q is another sentence. P, it's raining, it is a sentence. Q, it is Tuesday. For example, we can say that if the vacuum is moving, there is dirt on the floor, it can be one sentence. I have covered this area already, there is another sentence. Then how you model your sentence gives you actually a model. In this case, we say that sentence P, our model says that sentence P is true. And again, model says that Q is false. So based on our model, we said that this is our model. So if, for example, it is not raining, if for example there was an information which came from outside, it is not raining, then we can say, okay, Q is true. Why? Because in actual sense, Q was false. Sorry, it is Tuesday. If we say that if it is not Tuesday, then our model will result Q is true. Why? Because our model was saying that yes, the information it is Tuesday is false. So it means that if it is not Tuesday, it would be a true information for us. However, P, if it is not raining, then this would be a false information for us. Negation of that. So it means that here P is a simple P, where Q is, we can say it is a negation of Q. So it means that whatever information we will be getting from outside, our model would map it either directly or either as a negation. So if, for example, we say it is not raining, then it will come inside and it will be complementary. It is raining. So overall, we can say that okay, it satisfies our model. But the overall crux is that P we model it with something and Q we model it with something. So here there are two sentences which are very important. The model is an assignment of truth value to every proposition. So whatever sentence or proposition you have defined, you give them a truth value, either true or false. This is your model. So if we look at this can be one model, this can be second model, this can be third model, this can be fourth model. So it means that if we have this condition in our system, and if we have certain P and Q coming, our model will look for all possible models. Our AI agent will look for all possible models, but then it will also look at the knowledge base, that which model has been defined in the knowledge base, and then it will remove all of the possibilities and will only compare it with the model which is actually existing.
It's like loop, right? It's like
yes.
it's kind of loop out the process.
Yeah. So that's why if I come again to the knowledge base, I initially defined that knowledge base is combination of sentences, right? I can write it again that knowledge base, this is knowledge that the AI is provided about the world in the form of propositional logic, sentences that can be used to make additional inferences about the world. So it means that knowledge base is anything which you know about a certain problem, and then from that knowledge base you also make some more conclusions. For example, in the previous case, if you remember where we said that if Tyrion was doing something, Tyrion cannot visit Bronn and Jon, and then we also did some inferences that if he is visiting Jon, then something is happening. So it means that we do have some propositional logic, and then from those propositional logic, our AI agent should be trained enough that it can infer all the possible outcomes, so that it is intelligent enough to based on certain information, it can combine all the possible information. If I'm saying if it is not raining, I will not go outside. So if, for example, I can also say I'm not outside, it means it is not raining. So it means that all the possible different mean holding your ear from this side or this side mean come up with all the possible outcomes. Right. This brings me to a concept which is called entailment. Entailment means in every model in which sentence A is true, sentence B is also true. If, for example, I said that, if yeah, there is an example. So, if it did not rain, Tyrion visited Bronn today. Tyrion visited Bronn or Jon today, but not both, so it can visit only one. If it has visited Jon, this is the third condition. So, want AI to use three sentences inside our knowledge base and infer or draw conclusions or entailments. Mean from a certain knowledge, draw all the possible outcomes which are also true. So from this, I can draw one knowledge. If Tyrion has visited Jon today, it cannot visit Bronn today. And if Tyrion is not visited Bronn today, it means that it was not raining. So it means that if these statements are true, which we can take as alpha 1, alpha 2, alpha 3, if these three sentences are true, then the entailments, which are betas are also true. It means that it's very important based on certain knowledge. Clearly, your algorithm can look for all the possible solutions, compare it with the database, and do all the extra logic. For example, here it could have said that Tiran visited Braun. Where we said Tiran did not visit Braun today, right? If I say Tiran visited Braun, this is not an entailment, right? Why? Because this is contradicting the actual statement. It means that if beta is contradicting alpha, this is not entailment. So it means that at every point, we can check for entailment. And why it is important? This is important in two senses. One is to draw an extra conclusion. Then there is another thing. If to get certain information from the output, outside, if for example, you were having all this knowledge base, you only have this information. If the information was, it is raining today. If we say it is raining today, then you can take, your knowledge base will take that input and will compare it with all the entailments and will see if it can draw certain conclusion or not. So that's why entailments are very important, because based on certain inputs, then the knowledge base will give you desired logic or desired output. So there was second statement. We want AI to take different sentences and look for possible entailments. So it means that entailment is any logical outcomes that we can draw based on certain specific information we are given about a problem. Right. Now, moving a little bit further, like I said, that to draw entailments or to infer something, to draw inferences, to infer something that what would be happening. So the process of deriving new sentences from old ones, this is called inference. So here again we have an example. P, it is raining. Q, it is Tuesday. And from our model, we also know that P is true, Q is false. Previously we discussed this model. And there is a third sentence R, which says John will go for a run. Okay? Now, this was the information with us. Let's see it in terms of a knowledge base. So, this can be a possible information, but let's look at the knowledge base that we have. So, inside knowledge base, we were having these statements written. Like I said, that these complex statements written. So, this knowledge base tells us that P and negative of Q implies R. If it means that, what does mean? And also in the model we know we have P and we have Q naught, which means that P is true and Q is false. So it is not necessary that we write it like P true, Q false. It means if you will look at knowledge base, you will see two lines. One line is P and negative of Q implies R, and the second line you will look at, you will simply see P and you will simply see not Q. It means that P is true and negative of Q is true, right? Or Q is false. So if you see something this, I written true and I written true here again, but you will not see this true, you will simply see P and not of Q, which means that in this model, P is true and not of Q is true, because Q is actually a false statement. Okay, so now, as we said, implication, where this symbol was here. I mentioned at that time that there is one important information. If left hand side is true, right hand side is definitely true. This we can draw from this point. So it means that P true and negative of Q is true, or indirectly Q is false, then R would be true. So it means that if it is raining, if it is not Tuesday, John will go for a run. So this is something. So inference we can draw is R, that John will go for a run based on the information from knowledge base. So based on this information from knowledge base, we can draw this inference. But the question is how the AI algorithm will do that. Because here we can say, okay, this is our knowledge base, we can look at it and we can see and we can say that. But to knowledge base, it has this information, then it will take certain information from the output and then would compare what is happening. So that's why it is very important how to train AI to draw such inferences from given knowledge base, how to write, WRIT, how to write algorithm which can look at knowledge base and draw inferences or entailment. So it means that how we get an agent to do these tasks, how to infer or how to make entailments. Our goal now, so now what is our goal? Our goal now is to decide whether knowledge base, and you already know that this is a sign for entailment. Our goal now is to decide whether knowledge base entail alpha. It means that in this case, in our case, we can say that knowledge base entail R, because here we want to infer from one point to another point. So if, for example, this is your knowledge base and this was your entailment, we want to draw this entailment. So our goal now is to decide whether knowledge base entail any sentence alpha, and in our case we want to see that whether R entail by knowledge base, means whether the knowledge base has this information, whether the knowledge base is inferring this or not. So there are several algorithms to do this kind of mapping, to do this kind of inference, but the very simplest approach is model checking approach, which is somehow, in the model checking approach you will directly look at whether it belongs, this certain entailment belong to the model or not. Okay, so based on whatever knowledge base we have, like if you remember previously we said that this is your one model, this is your second model, this is your third model, fourth model. I mean, you can assign P as false, you can assign Q as false, or another model can be, you can assign P as false, Q as true. So these are all the possible models. So it means that the very first thing your algorithm will do will derive all the possible models. This would be the first step. Then the second step would be to compare those models with the knowledge base to look which model entails the knowledge base, and then it will do the final inference. Okay, so it means that in this algorithm, the very first step is check that alpha is true in every model in which KB is true. So it means that the very first step is to drive all the models and check if they are entailing, if the sentence entails the knowledge base. And we know that what is model? Model, like I've explained, it can be assigning certain thing, a true value or a false value. So if you have P and Q, you have combination of 4 models. Okay, so it means that here, if now we are trying to find entailment, and here we have 1, 2, and 3 things. So it means that we want to find entailment between these two. So let's take P, Q, and R. So here, if you see here, you can see that we have totally 3 variables between which we want to find entailment. Okay, so it means that the very first step is to write all the possible combinations. So it means that we can write these combinations, which we know for 3 cases it would be 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, and same goes for on this side. So it means that these are all the possible logics that we can get for 3 variables. Now we will check each model against the knowledge base. We will check each model against the knowledge base. So it means that if here we know that If left hand side is true, your right hand side must be true, definitely true. So here you can see that P is true, and if Q is false, I mean negative of Q is true. If Q is false, then R would be true. But in the first case, you can see that you have P false, you have Q false, and R false. This doesn't belong to the knowledge base. So it means that knowledge base is false. Similarly, if your P is false, Q is false, R is true, which is not the case. Why? Because clearly in the knowledge base we have this information. And why we have this information? Because these two are making our life easy. Two statements. If it was one, then there was a knowledge base, but we were unable to decide. But here clearly it says P is true and negative of Q is true. So it means that when P is true, negative of Q is true, which is actually false, then R is true. So this is the only case which you can see is true, false, R is true, so knowledge base is true. So it means that whatever conclusion we draw in the previous case was true based on our logic, but if you want to see how an AI algorithm will work, it can take all the sentences, it can assign them all the possible combinations, and then each combination it will be checking across the knowledge base, and then we will decide, okay, yes, this inference or this query was fine. So this would be final answer. Now, to make our life easy, because at the moment you can see that it is quite difficult to understand when it comes to employees or when it comes to bidirectional. So we want to make our life easy, and how it can be easy? We all know that if we have anything in terms of gates, AND gate, NOT gate, OR gate, then it is easy to solve. We know that. So we will study some rules where our main objective would be somehow find rules using which we can represent employees with known gates, AND or NOT or something. So let's see how we're going to do that. So these are called inference rules. Inference rules mean based on certain knowledge base, what outcomes you can derive is the inference, right? And now we will see there are certain rules. So how inference rule is written? You have a line, there is a statement on the top, and then from the statement, when what can be inferred is written in the bottom. So it's not numerator or denominator, but we can say on the numerator you will be having the main condition, and then in the denominator the inferred knowledge based on the condition. If it is raining, then Tyron is inside. So based on this, and this was one information, and then the second information was it is raining. So the first information of it is raining, Tyron is inside, and then at the same point you can see that this was a condition, same as the previous case. There was a condition, and then there was true information about the event. So we can say, okay, if it is raining, then Tyron is inside, and then the second information was it is raining. Then we can simply say, yes, Tyron is inside, definitely it is inside, right? So here you can see that if, then, and then another condition. So what does if then means? Which rule we have studied to which it corresponds, if then? Whether it is OR, whether it is implies, whether it is bidirectional.
Is it implies?
Implies, right? Because we say that in case of implies, we say if then. Okay. So this kind of inference rule is called modus ponens. Okay. So here we say that if it is raining, sentence is mentioned with the name alpha, implies if it is raining, then Tyron is inside, which is beta, and then together with this condition, you are having another useful information alpha, which means it is raining, right? So it means that beta is true. Time is in inside.
A question. You know, all these models we cover now. We cover economic and you cover a few models right now, yeah.
Sorry.
You know, you cover a few models with different roles, with different
Yes.
formulas. In real life, is it what we're using? Is it based on what you wanna implement, or the output you wanna get from the results you're looking for?
Yes, basically, you want to implement your logic, and the best way to implement your logic is normally we do with logic gates, right? So in this case, yes, your main objective is to develop certain logic. Then if you have some information, then you can easily say that what is happening. So for example, this was your knowledge base,
Yeah.
and if from the outside you get an information that it was not raining, then you can clearly say that Tyrion wasn't inside. So yes, base means your knowledge base will make your agent intelligent, then it will take certain input and will decide that
Based on
what,
the model.
yes, what
Formulas,
is,
basically.
yes, you can say it's a kind of formula. Yeah. We will also, not sure today, but from this it came to mind. I will show you an example where we will see that how a knowledge based system is very useful. It's a kind of game where you start from a puzzle game where you start from a certain point and you need to find gold. But on your path there can be like someone to eat you, or you can fall into the pit, and then you have also some information. And then using all those information, you keep on moving, and ultimately you reach to the goal. So yeah, in real you implement these logic, and that's why these are in inference system. If you know fuzzy logic systems, fuzzy logic system. So in fuzzy logic system we have certain rules, if then rules, and then if you say if price is high, charge my battery with low currents, so that profit is I don't pay much cost. So these kind of this is actually implemented in real life. So that's why we are studying these inference system. Similarly, there are many other logic that if, for example, renewable power is high and tariff is also high, sell your power to the grid. So this can be logic. So your system will keep on monitoring all the variables. So if I say if tariff was high, renewable was high, and then sell power to the grid. So each time it will be monitoring tariff, it will be monitoring power from renewables, and if both of them are high, then at that time it will be sending power to the grid and will be earning profit. So this is how we actually implement these rules. So modus ponens rules tells us that it simplify implies rule for us. So you can see that if it is raining, implies that then Terence is inside. So it means that if we are another information that if it is raining, then we clearly say that the inference is that Terence is inside. So if alpha implies B and alpha is true, then the inference is beta. Then the output is beta. Now the next thing is called and elimination. Terence is friends with Braun and Daenerys. Okay. With Dan.
It's a Game of Thrones reference.
Right.
Yeah.
So from here we can see that if he's friend with this and this, we can clearly say that this is also friend with this. So it means that we are eliminating some of the information which is not required. So Terence is friend with Braun and Dan. How are we going to write it? So in this case we have and we are going to eliminate something. So A and B. So we said that if alpha was like is friend with this and this, Terence is friend with Braun and then we simply taken that he would also be friend with Dan. So that's why this statement is alpha, this statement is beta. So we simply say that if you have A and B, you can simply write that it is simply the second statement B. Or in other words, we can say that one of them must be true. Okay, now is double negation. I know it's looking at Fraz's expression. I know it's slightly not difficult to. It's how I would phrase it. Yeah, slightly difficult to understand, but yeah.
To absorb the information now.
Yeah, but you have to actually.
Yeah. It's fast.
We'll do this and then we'll take maybe 2-3 minutes break and then we'll start. Double negation elimination. It is not true that Tiran did not pass the test. It is not true Tiran did not pass the test. So it means that we have two negations. It is not true Tiran did not pass the test. So it means that Tiran passed the test. Right? So negative will make it positive. So that's why we say that negative of negative alpha will give us alpha. And if you somehow visualize it, I'm trying to make the same logic which we do in digital logic design, where we say that A naught, how we define A naught, A and B, how we define A and B. So all these are the same thing. So if we say that if there is a NOT and we again take NOT, it will be the actual thing. So if, for example, I say that if I am passing A to a NOT gate and then there is another NOT gate, so the first NOT gate will make it negative, another NOT will make it positive. So that's why if you have information, if it is not true that Tiran did not pass the test, Tiran passed the test. So because did not true, it is not true, did not pass. Cancel each other, it means that Tiran passed the test. I could have written all these things directly, but then it was very difficult to understand. I mean, some of them, this is easy to understand, but with example, it makes more sense. Let's take 2 to 3 minute break and then we can begin again.
Hmm? How is it? I'm not sure.
Do they give you back
That's what I'm trying to do.
Huh?
I'm going to be checking on the back end.
What? They give you
Says
back?
no, this week I will ask to say the thing. I'll do some testing and make it. Good.
You sleep?
Me?
Yeah.
No, you can do it.
Why?
Hazy your eyes.
Why?
Actually, let's go.
You couldn't sleep? What up?
Much love you to eat your video.
Where you been, man? Where have you been? Last 2 weeks?
Too tired. Fasting and things.
You didn't come uni.
Fasting, part-time job.
Yeah, how's fasting been?
Sorry?
How has fasting been?
So right now I'm a bit busy, so going to work and sometimes having something breaking my fast like 10 in the evening,
Yeah.
come back from work.
What's been worse?
It's tiring.
The hunger or the lack of sleep?
Everything.
No, like
Lack of sleep especially.
yeah. What time do you wake up today?
Hmm?
What time did you wake up today?
I slept hardly like after
After that
yesterday
time?
I went to work, came back like 10, then had my things were like together like
Did you go to the Isha? No?
just prayed home
Okay, good.
and then slept, woke up, ate. Hopefully I have to do the same today.
Don't do it.
You have to.
You can do it. Oh, you're me. Where's the lecture? Where's Stavros' lecture? Yeah, where is it? Still, it's good to have it, right? I know, where is it? You recorded it, right? So upload it. Yeah, upload it.
What's the beef about it, you know?
You need it?
Hmm?
That was too.
Oh, basically, last week I came for the Names lecture, but I didn't come for Friday because it was like a second fast or something, right?
Last Friday.
Yes.
What happened on last Friday?
No, I don't know, I wasn't in. So I asked him to record it.
Yeah.
Last Friday just the lab, I think.
Yeah. I mean, nothing, no tutorial or anything. I record the tutorials fine. But, yeah, I wasn't in, so I asked Elmi to record it for me. And he hasn't uploaded it yet.
Last Friday, I think there was a lab.
There was, I think.
Liz two persons in like the 15 years age. And completed like home.
Are you coming in tomorrow? Okay. Do you want to come in? No, but are you coming in?
What's the point of coming? Like, so to come.
For attendance, I guess.
There is no point to be honest. Like,
True.
Because he said when I scan the said
it's better if I don't come because
we look.
if I stay home, I can at least finish the lab.
That's true. Oh, man. You'll save some train fare as well.
So what did you scan?
I don't have to worry about it because I buy like weekly tickets.
True.
So
Yeah, I forgot you work. Okay. Luckily, you know, the fasts are not too bad in terms of when we break them.
it's not about the process, it's about my timetables are really messed up now.
What is it? Oh, your schedule.
Yeah, just because I do part-time job,
Yeah.
I asked him access.
Well, you're not doing the night shifts, are
I
you?
have to do it because
What night shifts?
No one gives you access.
I'm in the part-time
You
job.
have to do
Yeah.
it yourself.
That was like payment.
Okay, yeah, I get that.
He doesn't know what he's talking about.
I don't have my parents here like you.
That's the
Oh,
problem.
days. It's okay, but you were able to come here. You paid for the plane ticket.
Very cool.
Rich back home.
It's a big problem. You know how to do blog
Yeah.
software, but he doesn't know how to do
Spoiled brat.
So this was double negation. So let's move to further. If it is raining, then TDN is inside. Again, here you can see that we have implication.
You personally.
What information we can get from this? We can say that it is not raining. Here it will say if it is raining, then TDN is inside. It is not raining or TDN is inside, right? So the same information we can extract is if it is raining, if it rains, then TDN is inside. So it means that it is not raining, so TDN is inside. So it means that this implication we can we can say that alpha implies beta. We can say that negative of alpha or beta. So we can clearly say that if we have alpha implies beta, we can say that negative of alpha or beta. If it is raining, Tn is inside. If it is not raining, it is not raining, Tn is inside. Because we have an if statement in the first case, and in the second case, we simply remove the if statement and we said that it is not raining. Then there is a possibility or Tn is inside. So this is called implication elimination. This inference rule is called implication elimination. Then moving further, coming to bidirectional operator, if it is raining if and only if Tn is inside. So it means that it is raining, definitely Tn is inside. So now we have a biconditional thing. So we can say that if it is raining, then Tn is inside, because this is if and only if statement. So we can draw two conclusions from here. If it is raining, Tn is inside, then T is inside. And there is another statement as well. If Tn is inside, then it is raining. So it's just the same statement, but we are trying to convert them into known logic. So it means that here we were having a bidirectional logic. We converted it to two one-directional logic, implies sign. So if it is raining, Tn is inside, and if Tn is inside, it means that it is raining. So here you can see that we have an implies sign, again implies, and we have an and. So it means that if you have a bidirectional alpha beta, we can say that alpha implies beta and beta implies alpha. So indirectly, as I initially told you, that alpha implies beta. So double bidirectional means this can imply this or this can imply this. So it's the same thing. So it means that we can resolve it in this form. And you can see that once we have this form, we also came to know from the previous step, implication elimination, where we said that alpha implies beta. So negative of alpha or beta. So it means that we can further solve it in terms of further known parameters. So here you can see that here we said if we have an imply, we can say negative or beta. So it means that once we have a bidirectional thing, we can simply convert this one further with implication elimination rule, and also we can split it further with implication elimination rule. But this was biconditional elimination. We are simply eliminating the biconditional operator. Okay. Now this brings me to De Morgan's law. I'm not sure if you have studied it somewhere in the mathematics.
What's
Yeah,
called?
let's say how to reduce the ordinary logics,
Yes.
type of logics.
So it is not true that both Tirian and Braun passed the test. So it is not true that Tirian and Braun passed the test. What can be a possible logic? The logic is either Tirian did not pass the test or Braun did not pass the test, because we clearly said that it is not true that both Tirian and Braun passed the test. So the only logic that we can get from here is Tirian did not pass the test or Braun did not pass the test.
Is it an actual logic or something like that?
So that's why we say here, so you can see that there was not sign, and here it was Tirian and Braun, alpha and beta with a negative sign, right? So it means that we have alpha and beta with a negative sign. What does it mean? It means that here the and has been converted to or by opening the negative sign. This is what a De Morgan's law is. If we in here we have written it in this specific form, but we if you know this is a familiar form. A and B naught is equals to A naught or B naught. So this is the familiar form which we get from mathematics. Okay. So this is called De Morgan's law. If you have not operator and two things are and, then if you want to open them, you simply split the not on each sentence, and then the operator which is and would also be inverted to or. This is how you interpret it. So this property is called De Morgan's law. Okay. Now, in this case, there was one condition. It is not true both and B inferred something. Now we will take the same example, and we will try to put it in a different way. It is not true that Tyrion or Braun passed the test. Previous case it is not true that Tyrion and Braun passed the test. So from here we can easily say that Tyrion did not pass the test and Braun did not pass the test. So it is not true that Tyrion or Braun passed the test. So if you want to convert this, we can say that Tyrion did not pass the test and also Braun did not pass the test. So the same thing. Previously we said that when you have an AND operator with a NOT, it gives you two NOTs with an OR operator. In this case you can see that you have an OR operator and there is a common NOT, so it will give you two NOTs combined with an AND. So, sorry? Okay. So here you can see that alpha or beta with a NOT gives you not alpha, negative of alpha and negative of beta. When you will later read these slides, these examples will make sense and will give you more good idea, even if it is not being absorbed at this time. Okay. Now, distributive property. Again, we know this property, right? So A and then inside the bracket it's B or Y. So we can write that A and B or A and Y. It's same as A into B plus C. It's AB plus BC, right? So A and B, then plus A and K. So this is called distributive property. So again, we are trying to see this so that later on when we have certain information coming as an input, coming as a percept, based on the logic that we have, we can take that input, put in our logic, try to manipulate it and come up with certain. So the same property holds in the other way. So if it is A plus B and Y, so it can be A or B and A or Y. So the same distributive property in the previous case, it was multiplication on addition, and now it is addition on multiplication. Okay, now we have studied some rules, inference rules. Now we are trying to get towards a resolution, mean base. This would be again a kind of inference rule, but we can say that if you have certain information, so here you can see that we have certain information, how we get a resolution out of it. So here it says that Braun is in the throne room or Dan is in the library. So this was a conditional statement, and then Braun is not in the throne room. So what we can get from this? So the first says that Braun is in throne room or Dan is in library. And then it says that Braun is not in throne room. So it means that, what does it mean?
It's in the library.
Yes. So it means that either this is true or this is true. So if this is false, this would be true. So that's why we say that Dan is in the library. Okay? So it means that Bron is in the throne room or Dan is in the library. And then there was another statement which said that Bron is not in the throne room. So the only other possibility for getting true is that this is the other person is in the library. So you have alpha or beta, and then you have negative of alpha, or P or Q, and then negative of P. So it means that from this, what we can infer? We can infer that Q is true. Why? Q is in the library. So we can say that we have Q. So this is how, if you have certain statements, you can get to a conclusion. You can get to a resolution that based on all these, this conclusion can be drawn. So similar, if we want to extend it, so previously we said that P, Q and negative of P, so the output was Q. So in this case, if we say that P or, if Bron is in the throne room, he's in the library, or he's in another room, he's in another room, and so on. And then we say that what was the name? Bron, yeah. So then finally, if we say that Bron is not in the throne room, we can say that okay, Q1 is in the library, or Q2 is in the other room, or Q. So it means that we can extend the same resolution for multiple things. So it means that we have to look at here, and we have to look at the second logic, and we have to cancel the one with the negation. So this with this will cancel out each other, and you will be left with the other part. So it means that these can be the possible conditions at that time, right? So it means that your agent, if you give the agent this information, the agent will look for these possible conditions. Okay, so now in the previous case, you can see that you were having one condition, complex sentence, and there was a simple sentence. Now we will look for, that's why here you can have a condition and then a simple variable. Now we will look for another version of resolution where in both cases you have conditions. So Bron is in the throne room or Dan is in the library. Then Bron is not in the throne room and Tyrion is sleeping. Then we have another person which came in. Okay? So now the thing is, you can see there is one negation here. Bron is in the throne room and Bron is not in the throne room. Means this would be cancelled. Which things are left? Dan is in the library and Tyrion is sleeping. Right? She is the lucky guy. So it's in the library and Tyrion is sleeping. So it means that again, if I take it as P, this is negative of P. If I take it as Q, if I take it as another variable, so these two variables will stay and the other. So we keep on looking for contradictions, negations, so as to come to certain point. Because this is how, even if being a human, we think in the same way. We say, okay, no, this is not the option, this is not the option, okay, this is the option. So we have to train or we have to make our system think the same way. So you can see that P or Q, and then negative of P, R. So finally this would be cancelled, so it would be Q or P. Mean Dan is in library or Tyrion is sleeping. Okay, now we can extend this logic. So person number one is doing something or doing something and so on. Similarly, here we said that he's not doing this thing and we introduce another person. So this would be cancelled and it would be Q or Q2 or R1 or R2 and so, right? This is how we keep on extending or developing, inferring from any given logic, any given information, so that if we to come to a conclusion or to come to an output.
You know this logics when they develop it, for example, code, they use this kind of
They use this kind of logic, yes.
yeah, based on their client.
Yes. Now we have conjective normal form. Conjective normal form, you can see logical synthesis, that is a conjunction of clauses. So you can see that an example here is A and B and C are not. Here you can see that if you have C and F form, you don't have any imply, you don't have any by conditional thing. That's why we say that whenever you want to understand a knowledge base, the very first thing is eliminate by the conditionals, because we want to convert our knowledge base to a conjunctive normal form. So it means that turn biconditional into simple conditional. A implies B, and B implies A. This would be the first step. Then eliminate implications. We can eliminate implications. We already know if A implies B, we have said that negative of A or B. So negative of A or B. Then the further step is move not inverse using De Morgan's law. So if you have not on the top, take it to each component so that you can simply put 1 and 0, or you can simply put in a condition and try to solve it. For example, if you have this, turn not of A and B into not of A or not of B. Use distributive law to distribute or wherever possible. So it means that whatever properties we have studied, we have to apply all those properties to a certain knowledge base to get to this CNF form, so that once we have a CNF form, we can easily reach to a conclusion. So if, for example, A and B was something, some input from a sensor, and this is our knowledge base. We can take A and we can take B, and we can say, okay, based on these input, this is the output, so take certain action. So it means that it's very important to convert your system into CNF. As I said that it's very important to your resolution. It is easy to make inference or conclusion when you have your system in this specific form. So if you have P or Q imply R, so it means that the very first thing, so this is an example that we have just studied previously. So if you have P or Q implies R, take it as A implies B. So it means that negative of A or B is the implication. So it is running, the T is inside, it is not running, or T is inside. So alpha implies B is negative of alpha or beta. So the same thing, negative of this or R. So it means that the first step was, because in this case there was no biconditional, so we eliminated the implication. Then we applied De Morgan's law, and we took this negative side inside, and then finally you can see that we can apply distributive law. So you can see that this will come with P as an R, and then between is M, and then Q. So it means that finally you have a distributive law. So it means that based on all this, now you can easily, if you have certain condition, you can easily decide based on knowledge base that whether it is in the knowledge base or not. So here again the same example that we have seen is P or Q and then negative P or Q. So what would be the answer?
Q or R?
R. Yes, why? Because P and P would be cancelled out. Now in this case, what would be the answer?
QRS.
So
You know, we cancel out
Q,
V
R.
and V, then V and V,
Q, and S.
Q on
and S.
and S.
Now you can see S is 2 times, but we don't need to write it 2 times. It's
No,
just S is S.
So you have to cancel out as well.
Sorry,
No, no, no.
you have to what? Sorry.
He said do the two S's cancel out.
No, no.
Just the-
S's would cancel out when one is S and one is not. So 1 times 0. So here they both are S1, S1. So 1 times 1 is 1. So right, it would be simply an S. So that's why we say that it's Q, V, S, V, R, V, S. But then it's Q, V, S, V, R. Because we can, if S is 1, at both places it will be 1. So it is wise that we just write 1 instead of 2. Yeah, it makes sense. It's 0, right?
Oh.
Because it's and this is called empty clause. Yeah, there is short conclusion and let me see if I should go. Let's leave it for the next class. But in the meantime, do read these lectures so that you know when we are doing anything direct, you know what it is. Okay. Now we have studied mainly all the rules. Now the only thing we would, like I said, that what is the reason for studying these rules is if we get any sentence, we want to see that whether it belongs to knowledge base or not, whether we have, if there is certain information based on this, we can say if this sentence is true or not. So now the next step is that we're going to see that how we link certain sentence to a knowledge base based on all the information that we've studied and how to verify.